Hey physics students, we're back with another edition of Rapid Review for Honors Physics. Today the topic is impulse and momentum, which are related concepts. I will remind you that momentum is mass times velocity, it's a vector, and I'd like you to consider a single object being hit by an external force. Here I show mass m1, it's probably a baseball, and it's getting hit by a baseball bat. Let's assume that the force ultimately is from right to left, so that we have a problem in one dimension where, of course, to the right is plus and to the left is minus. Wow, that's a mess, but you know what I mean. Okay, so I want to emphasize that this is a single object. Even though something's colliding with something else, I have declared my system boundary to be a single object. Therefore, the baseball bat is an external force. I'm going to apply that force over a time delta t. Here in the lower right, I've put a graph of the force times and the force as a function of time, and you can see I made it a little square shape, which means I'm assuming, at least for simplicity right now, that the force is constant with time. Now we define impulse as force times time. It's a vector, impulse is, and the direction of the impulse is the same as the direction of the force vector, as you might have guessed. Because time is a scalar, if I multiply these two things together, I get a vector, everything's cool. Notice that if I take force in newtons and time in seconds, my units are Newton seconds, right? Newtons times seconds. All right, so now let's look at an example where a bat hits the ball. I will remind you we're looking at a single object, the ball, and the bat is external. Okay, so we have an initial velocity, and then at some point we have this impulse applied from the bat, and then finally there's a final velocity. Now what I'm going to claim is that the impulse applied by the bat is equal to the change in momentum of the ball, right? So first of all, you might question, how could this possibly be? Because you just told me impulse is in Newton seconds, and P, as we learned earlier, is kilogram meters per second. Well, don't worry. You can freeze the video and look at this and convince yourself that 1 Newton second is indeed equal to 1 kilogram meter per second. They are the same thing. They're just two different ways of saying the same thing. The cool people will use Newton seconds for impulse, and they will use, for momentum, they will use kilogram meters per second. You should do the same. Good habit. But I probably wouldn't mark you wrong if you interchange them, because you'd be technically correct. All right. So a practice problem might be, this would be very typical of a problem. Here's a baseball with an initial velocity moving to the right, and a baseball bat hits it with some impulse, and you are asked what is delta P, right? So you have to calculate the impulse. You're essentially given the initial momentum, because you just have to multiply two numbers together. Watch your units, use kilograms and meters per second. The impulse is easy to calculate, right? Newtons times seconds. And when you solve for the final velocity, you will get, ding, 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 here's the answer, minus 38 meters per second. If you got a different answer, you made the mistake that you were sort of set up to make here. If you look carefully at the statement here, it says the bat applies a force of 840 newtons over a time period. Note that that force is pointing to the left, right? You can see that in the picture. I think to be more fair in the question, I might have said a force of negative 840, but all I gave you there was the magnitude. The point of all this is be careful, watch your pluses and minuses, because momentum is a vector. Okay? Now, let's question why. Why would this be? Why would it be that force times time is change in momentum? I will answer that later. But first, I want to talk about the more realistic case of something being hit, instead of constant force over time, you know, like you can imagine this tennis racket, the ball squeezes, the racket deflects. It takes some time. It's a fraction of a second, but it does take some time. So what that graph would look like is what I'm showing here. This might be, let's say, happening over a period of, I don't know, less than 1/10 of a second, as you can see in the picture. That would be more realistic. I've done measurements in class with a force sensor and something to hit it with and stuff like that. And this illustration is actually pretty realistic. Okay, so how do we get that? How do we get the impulse? Well, the answer is we just have to calculate the area under the curve. And we have seen this before, area under the curve, or if you're studying calculus, the integral, right? Area under the curve can be used for so many different things. Here, if I want to find the impulse given a force time graph, all I have to do is find the area under the curve. It doesn't matter whether it's shaped like that or something else. It's simply area under the curve. How do I know that? Oh, you've seen this slide before, right? So you can think of the curve as a bunch of little pieces. I do want to credit the John Coley textbook, which is my favorite physics textbook for this class, and that's where I got this illustration from. Okay, so I think I owe you an answer to why delta P is force times time. And I do a quick derivation here. Instead of reading it, I'll let you read through it if you want to freeze the video. It comes from the definition of Newton's laws and from from Newton's law and from the definition of acceleration, which is change in velocity over time. Let's end there. I think that's probably all I need to say about impulse and momentum. In another episode, we're going to be talking about collisions in 2 dimensions.